Having looked at the double angle identities for cosine, we're now going to have a look at the double angle identity for sine. And as we saw with the three double angle identities for cosine, you're not going to be expected to prove them, rather you're going to be given questions where you're asked to apply them. However, if you can follow the derivations through, that might help in your understanding. So, first of all, if you cast your mind back to the one of the previous rules we looked at, which was that sine squared theta plus cos squared theta equals 1. So the sine squared of an angle plus cosine squared of an angle equals 1. We can actually, instead of writing theta, we could write in 2 theta. So we've got this relationship here, sine squared 2 theta plus cos squared 2 theta equals 1. And we can rearrange that such that cos squared 2 theta equals 1 minus sine squared 2 theta. So we'll be coming back to that in a minute. From the previous session on the double angle identities for cosine, this is one of the identities that we looked at. Suppose then we square this. So if we square both sides, we end up with cos squared 2 theta equals 1 minus 2 sine squared theta all squared. So we've now got two equations. Equation 1 here equal to cos squared 2 theta, and equation here 2 equal to cos squared theta. So what we can do is set them equal to each other here. Then we can expand the right hand side to yield 1 minus 4 sine squared theta plus 4 sine to the power 4 theta. From there, if we rearrange it, if we take the 4 sine squared theta over to this side and this over here, the ones will cancel out, leaving us, if we move this over here, to sine squared 2 theta. We can then factor out 4 sine squared theta, leaving us with 1 minus sine squared theta is equal to sine squared 2 theta. And from the relationship cos squared theta plus sine squared theta equals 1, we should be able to see that this would be the same as cos squared theta, so we'd be left with 4 sine squared theta cos squared theta equals sine squared 2 theta. And we can then take the square root of both sides, leaving us with 2 sine theta cos theta equals sine 2 theta. And that indeed is the double angle identity for sine. So we will look at here part C and D of a question which we started in the previous video. So if you haven't done the previous video, before you start this, it is worth trying to find out what cos x is. So given that sine x is 3 over 4 and it's an acute angle, if you haven't already done part A and B, first thing you should try and do is find cos x and then have a look at these two parts here. So for the first one, sine 2x, well, we can see here we're just going to apply the double angle identity here for sine, and we previously calculated using sine squared theta plus cos squared theta equals 1 the angle for cos x here. So we'd previously shown that cos x equals root 7 over 4, so we can just substitute in 2 times sine x times root 7 over 4, and we can expand that to get 3 root 7 over 8, which is going to be the exact value. For part D, tan 2x, again using the formula tan theta equals sine theta over cos theta, we are going to combine our answers to the previous question. So we've just shown that sine 2x equals 3 root 7 over 8. And again, in the previous video, we used the double angle identity for cosine to show that cos 2x equals negative 1 over 8. So we've got this ugly expression here. We can say that dividing by negative 1 over 8 is the same as multiplying by negative 8 over 1. The 8's will then cancel out, and we will be left with negative 3 root 7. So you can see at the top here we've got all three double angle identities for cosine as well as the double angle identity for sine. We are told that cos theta equals 4 over 5, and in radians we are told that theta is between 3 pi by 2 and 2 pi. So what is significant about this is the fact that we are looking in the fourth quadrant. So we're looking at angles between in the fourth quadrant. So that's just something to bear in mind. Sine theta then is part A, what we're asked to find, and for part B, cos 2 theta. So have a go at this by yourself, and then we'll go through it together. Part A, sine theta, we can work out then using the trusted formula sine squared theta plus cos squared theta equals 1. So if we substitute in for 4/5 and square it, we can rearrange to get sine squared theta equals 1 minus 16 over 25, which is 9 over 25. So we're going to need to take the square root of this to find sine theta. Now the square root of this is going to be plus or minus 3 over 5. However, because we are told up here that theta must be between 3 pi by 2 and 2 pi, that tells us we're looking at the fourth quadrant. And if we're in the fourth quadrant, we can infer that the value of sine will be negative. So therefore, sine theta will be negative 3/5. For part B, we're asked to find cos 2 theta, so we're going to have to use one of these three double angle identities. We're told that cos theta equals 4/5, so therefore we're going to use the double angle identity which relies only on cos theta, which we can see is the second one. So take our value of cosine theta, which equals 4 over 5, and substitute it into this formula, and we can solve that to generate a value of cos 2 theta of 7 over 25. Next question then, you are asked to solve the equation sine 2x equals sine x for values of x between 0 and 360 degrees. So again, have a quick get at that yourself and then follow through the solution. We're asked to show that sine 2x equals sine x. So we can take the double angle identity for sine x, which is sine 2x, sorry, which is 2 sine x cos x equals sine x. Now, don't be tempted to cancel out the sine x here, that won't work. What you're going to have to do is, first of all, rearrange. So if you take the sine x over to the side, and then you can factor out the sine x. So if you factor out that, that gives you sine x brackets 2 cos x minus 1 equals 0. And from here then, we can look at the two solutions. So the first solution will be sine x equals 0. The second solution will be 2 cos x minus 1 equals 0. So if sine x equals 0, remember we are looking at values between 0 and 360, then x must be 0, 180 and 360. Alternatively, if 2 cos x minus 1 is equal to 0, then we're going to end up with cos x equals a half, and consequently we will be able to see that x must equal 60 degrees or 300 degrees. So it says solve the equation, so we need to look at all the solutions. So in total, 0, 60, 180, 300 and 360 degrees. Final question in this session then is pretty tricky, but you might want to have a go at it for a bit of a challenge. So we're asked to prove that 1 plus tan squared x times cos 2x is the same as 1 minus tan squared x. So have a go, or just follow through if that is a little bit too intimidating. First of all then, we can break it down into the component parts and think about what we do know that we can substitute into there. So we know hopefully that tan squared x or tan squared theta we can write or express as sine squared x over cos squared x. And also cos 2x here we can recognize using the double angle identity. One of the forms we can write it as is 2 cos squared x minus 1. And similarly here we've just substituted again for tan squared theta equals sine squared theta over cos squared theta. We can then expand, so 1 times 2 cos squared x gives us this. 1 times minus 1 gives us minus 1. Here, if we multiply sine squared x over cos squared x multiplied by 2 cos squared x, the cos squared x will cancel out, leaving us 2 sine squared x, and then this times minus 1 gives us this. So we know that that equals 1 minus sine squared x. So cos squared x. If we then cancel out, rearrange, we can take the 1 over to this side. These two will cancel out, so we'll be left with 2 cos squared x plus 2 sine squared x equals 2. If we divide 3 by 2, we end up with one of the rules that we looked at the very beginning of the session, or the section on the unit circle, which is sine squared x plus cos squared x equals 1. Therefore, we have shown the relationship between those two expressions.